Welcome to a journey through the evolution of space. Measurements show that light from distant sources shifts in wavelength as space expands, a process that began billions of years ago. This measurable expansion has steadily altered the positions of stars and galaxies, leaving behind clues in the changed hues of ancient light. Recording these changes is more than just collecting scientific data. It is a story written in time. The gradual transformation of light reveals how matter, once tightly clustered, has dispersed into the complex structure that underpins the history of everything that exists. At the same time, our own presence becomes part of this narrative, a small yet curious element in a chronology that stretches beyond everyday life. Today we'll explore how slow but relentless expansion has shaped the distribution of all surrounding matter and structures. Imagine standing beneath a clear night sky and realizing that the stars you see are not stationary. They're a part of a story of constant change. Today we'll trace how space stretches over time. Distant galaxies with their gentle glow will appear to drift away from each other. This motion is more than objects wandering through the void. It's the expansion of space itself. This effect is measured through a phenomenon called redshift, where light shifts toward longer, redder wavelengths as it travels through ever-growing space. Our journey begins with an observation made several decades ago when astronomers noticed that light from distant galaxies arrived stretched and shifted toward red. Think of it as watching a familiar pattern slowly change its hue over time, revealing that the distance between us and those far-off points is increasing. The first measurements were akin to watching a simple balloon inflate, each point on its surface moving away from the others as it expands. This observation provided the first clue that the universe is not static, but is constantly expanding. However, this is not just about galaxies drifting apart, but also how this expansion reshapes the very structure of the universe. In its youth, the universe was dense and filled with the raw materials needed to form stars. Under such conditions, gas clouds rapidly collapsed, giving birth to bright, energetic stars. But as space expanded over time, this material became more diffuse. This gradual thinning of matter meant that the conditions once favorable for active star formation became less ideal, leading to a slow decline in the birth of new stars. But more on that later. This thinning of matter plays a crucial role in cosmic evolution. As galaxies move apart and their constituent materials become less concentrated, the energy needed to ignite new stellar life becomes less accessible. Over time, the universe transitions from an era of vibrant activity to one where old stars age and fade, and the bright birth of new stars becomes a rare event. This shift not only changes the shape of galaxies, but may also have profound consequences for planets orbiting these stars, shaping the foundation of a quieter and more isolated cosmic future. Numerous pieces of evidence support this unfolding story. Astronomers use multiple methods to piece together the puzzle of expansion. By measuring the redshift of countless galaxies and using so-called standard candles, objects with known intrinstic brightness, they confirm that the farther an object is, the faster it is receding. Observations over the last century even suggest that this expansion is accelerating, adding to the mystery. The idea that space itself is not only expanding but doing so at an increasing rate brings us closer to understanding the fate of all cosmic structures. As the stretching of space lays the foundation for cosmic evolution, This process influences everything, including the mechanisms that create stars and ultimately lead to their extinction. In many spiral galaxies, vast clouds of gas and dust serve as nourishment cradles for new stars. These nebula, acting as stellar nurseries, contain the raw materials necessary for star formation. Under the force of gravity, denser regions within these clouds begin to collapse. As the gas condenses, its temperature rises, eventually reaching the point where nuclear fusion ignites at the core. And this marks the birth of a new star, a process that continually unfolds within the spiral arms where fresh material is abundant. Unlike them, elliptical galaxies present a completely different picture. Over time, the active processes of star formation in these galaxies have almost exhausted the available gas, leaving behind only an older population of stars, remnants of an era when conditions were more favorable for the birth of new celestial bodies. This is further exacerbated by the ongoing expansion of space-time. Since there is little interstellar gas left to fuel new formations, these galaxies are characterized by dim light and an aging stellar population. The life of a star is defined by the gradual consumption of its nuclear fuel. In its early stages, the energy generated by nuclear fusion sustains its brilliance. However, as the fuel depletes over millions or billions of years, the star's power diminishes. Depending on its mass, a star may end its life in a dramatic explosion or simply cool down and fade away. Regardless of the path taken, the eventual extinction of stars is a natural consequence of fuel exhaustion. This process not only marks the end of an individual star's active life, but also contributes to an overall decline in star formation within the galaxy. As the stellar population of a galaxy ages, significant changes take place. In regions rich in gas, star formation continues uninterrupted, replenishing the galaxy with young, bright stars. However, when gas supplies dwindle, as observed in elliptical galaxies, the formation of new stars slows dramatically. Over time, the absence of a steady influx of new stars leads to an accumulation of aging, dim stars. And this transition transforms once vibrant regions into areas where processes that once fueled star birth have effectively ceased, gradually creating a cosmic void. As the energetic cycle of star birth and decay follows the rhythm of cosmic time, the universe enters a phase of long, gradual dimming. Even the most resilient stars, red dwarfs, known for their astonishing longevity, will eventually exhaust their nuclear fuel. In these prolonged twilight years, the relentless march of time turns luminous star clusters into dimming, cooling remnants. Red dwarfs, burning their fuel at a measured pace for trillions of years, gradually lose the energy that once defined their glow. With each passing epoch, countless stars across galaxies age, their brightness fading, and the cumulative effect leaves what once was a brilliant cosmic tapestry increasingly muted. The slow fading of stellar populations foreshadows a future in which the dynamic processes of star formation will come to an end. As stellar lights burn out one by one, galaxies transform into clusters of ancient remnants. The silent presence of white dwarfs, the dense cores left behind after nuclear fires extinguish, stands in stark contrast to the explosive beginnings of the parent stars. Beside them lie neutron stars, the ultra-dense remnants of stars that once survived cataclysmic supernovae, and the enigmatic black holes, whose gravitational pull defies all explanation except through quantum effects. These remnants further emphasize the inevitability of this long twilight. No matter how stable a star may seem, it too will succumb to the slow, inexorable process of fading. As the light of the stars fades, the universe undergoes an even deeper transformation. With fewer active stars radiating energy, the overall temperature of the cosmos steadily declines. In this scenario, often referred to as the Big Freeze or heat death, the energy that once drove the dynamic evolution of galaxies dissipates into the cold vacuum of space. Over incomprehensibly long timescales, the remnants of stellar fires cool to absolute zero. Even the supermassive black holes that once dominated galaxy centers will not escape this fate. Through processes like Hawking radiation, they will slowly evaporate over periods estimated at around 10 to the power of 100 years. The chilling descent to near absolute zero creates an environment where all active processes cease. With energy so thinly spread across the cosmos, the once brilliant engines of star formation no longer ignite. The universe sinks into a state of deep emptiness. In this quiet era, the universe appears almost static. A vast expanse where time continues, but no significant changes occur. The Big Freeze leaves behind only cold, inert matter, slowly fading into darkness. In stark contrast to the slow decline of the Big Freeze, another scenario envisions a far more violent end. If dark energy, the mysterious force accelerating the expansion of space, continues to intensify, it may eventually overcome even the strongest forces binding matter together. In the Big Rip scenario, dark energy reaches a breaking point where its repulsive influence tears apart galaxies, star clusters, and ultimately matter itself. Initially, galactic clusters would disintegrate as the gravitational glue holding them together weakens. Then entire galaxies would be destroyed, with stars and planets drifting off their orbits as gravitational bonds are permanently broken. This progression is both dramatic and systematic. As dark energy's influence grows, even atomic forces that hold molecules together could eventually fracture. And in this scenario, disintegration begins on the largest cosmic scales and cascades down to the very smallest components of matter, including protons themselves. If the current rate of accelerated expansion persists, predictions suggest that the Big Rip could occur in about 10 to the power of 22 years. This cataclysmic event would tear the universe apart, leaving nothing intact, and puts a definitive conclusion to the cosmic narrative. As thought-provoking counterpoint to the Big Rip, another theoretical possibility suggests that the universe could reverse its expansion altogether. If the balance of certain yet unknown factors shifts, gravity might eventually overcome the outward push of dark energy, forcing the cosmos to contract once more. In this hypothetical scenario, often referred to as the Big Crunch, the entire universe gradually collapses back into a single ultra-dense point. As matter and energy are compressed into an ever smaller volume, conditions become extreme enough to trigger quantum processes that defy conventional physics. At this point of extreme compression, the laws of physics as we understand them break down. Quantum fluctuations and other exotic effects dominate, potentially laying the groundwork for a new beginning, a new Big Bang that resets the cosmic cycle. This cyclical model of the universe presents a vision of endless renewal, where each phase of expansion is ultimately followed by contraction, and the cycle repeats infinitely. Though highly speculative, the Big Crunch reminds us that the universe's fate may not be a simple one-way journey into oblivion, but rather an intricate process with the potential for rebirth. While the fate of the universe unfolds over trillions of years, the challenges facing our own planet are immediate and pressing. The grand cosmic narrative, filled with slow decline and dramatic distant cataclysms, stands in sharp contrast to the rapid transformative changes happening on Earth. Climate change, pandemics, and various technological catastrophes define the future of human civilization on timescales we directly experience. Though insignificant compared to the vast cosmic erasure, these issues are critical to our survival and well-being. Addressing these Earth-scale challenges requires a dual approach, mitigating immediate risks while also considering the long-term consequences of our actions. The same scientific inquiry that helps us understand the distant fate of the cosmos also guides our efforts in environmental protection and global resource management. This serves as a simple reminder that while the universe is vast and its evolution spans eons, the choices we make today have an immediate impact on the future of life on our home planet. History is filled with examples of problems and phenomena that were unforeseen in their time. In the distant year 1900, many of today's threats were unimaginable. Likewise, in the coming decades, challenges and opportunities may arise that we cannot yet conceive. These unknown unknowns serve as a powerful reminder that our understanding of the universe and our own existence remains incomplete. The story of the cosmos is not merely a tale of predetermined outcomes. It's an ongoing dialogue between observation, theory, and an ever-shifting landscape of possibilities. Being open to the unexpected is essential for progress. Whether refining our models of cosmic evolution or developing new technologies and policies to address global issues, the spirit of exploration must remain alive. The speed of light is one of the most fascinating and mysterious concepts in the universe. It's considered the cosmic speed limit, beyond which nothing can move faster. However, what if I told you that it's possible to reach this incredible speed? While it may seem impossible, the laws of physics make it possible. In this video, we'll explore the fascinating world of the speed of light and how you can get closer to this incredible speed. So fasten your seatbelts and get ready for a journey into the unknown as we explore the limits of what's possible in the universe. First, let's recall what speed is and how light works. So in physics, we call speed a certain value equal to the distance an object travels in a certain time without an exact direction. When an object moves, it increases its mass and the level of its kinetic energy. So the faster it moves, the more mass it will gain and its energy will increase. Therefore, for example, the faster a space rocket moves, the greater the scale of destruction if it collides with a meteorite body, and the more energy will be consumed. In particular, objects can change their speed depending on the medium and its molecular composition due to friction. So this all works for objects that have mass. But what about particles that have no mass, like photons? Let's turn now to what we know about light. Light is an electromagnetic wave resulting from the emission of energy from heated bodies that are perceived by our eyes. However, light is probably also a wave and can be described as a stream of massless particles or quanta photons. Light has a speed of 186,000 miles per hour, and in a cosmic vacuum, it's the likely speed limit for the entire universe. This is what Albert Einstein's fundamental work, which changed the way we understand our universe, tells us: general relativity. If we summarize this theory in one sentence, its main idea is that gravity is a curvature of space, not a force that acts on all objects, and the laws of physics apply equally everywhere. But what does this have to do with light? According to GR, light is constant. That is, it always has the same speed and is probably the fastest phenomenon of all. The reasons for this are the absence of mass of photons and the absence of light moving along the timeline. According to GR and the parabolic model of Hermann Minkowski, Einstein's teacher, time is unified, meaning that there are no separate time and space. Our universe has 4 dimensions: 3 spatial, x, y, and z, and a temporal, t, dimension. Since space is one, everything in it is interconnected. Therefore, depending on your location in space-time, you interact with time and space differently. Let's imagine this using a simple coordinate system with a time and space line. If you're sitting here watching this video, for example, you are moving only in time. Your position in space does not change and you have no speed at all. However, if you decide to go to the store, then you'll be moving in both time and space. It's precisely because of the fabric of space-time we cannot synchronize watches because of the time dilation. This was also proven by scientists in 1971. The researchers placed hydrogen clocks in airplanes on the ground and flew around the world. After landing, it turned out the clocks on the airplanes were running slower by about 1/1,000,000th of a second. Light, on the other hand, moves only in space. It does not feel the influence of time, so if we were to put a clock on it, it would seem to be suspended. Moreover, since light has no mass, it's not affected by gravity. However, if it passes near a black hole or a star, or more precisely along the geodesic lines of space-time near a massive body, its path and energy consumption increase and curve, but its speed remains constant. So if the speed of light is constant and photons are not affected by time, especially in space, how can we achieve or even surpass it? An object with mass, like you and me or a spacecraft, cannot move at the speed of light because it would require infinite energy. However, interestingly, there is another reason. We are already moving at the speed of light. We learned this from Minkowski's model. The faster we move, the slower our clocks go. However, since we have mass, time affects us and we're not physically moving at the speed of light. Our speed is scattered between time and space. Even charged particles cannot reach the speed of light because they also have mass. Scientists are trying to accelerate subatomic particles to the constant of light using linear accelerators with the help of an electromagnetic field, but their speed is always 99.99%. However, at the end of the 20th century, scientists discovered a strange phenomenon, namely the so-called FTL, the movement of particles several times faster than photons. Thus, while observing the galaxy M87 and its jet, a beam of ionized matter ejected from galaxies at high speed. A group of researchers took several pictures of the jet. They noticed that the jet seemed to be moving faster than light. However, this is probably just an optical illusion caused by photons that were emitted later from almost the end of the jet. So it seems to us the light from it travels a shorter distance. Moreover, there's another phenomenon in space that can accelerate particles to the speed of light, but this time it is true: magnetic explosions. When magnetic fields collide with each other, they can often become entangled. If the tension between them increases greatly, they will break apart, which will throw all the charged particles away in an ultra-high speed. This process can be considered a natural particle accelerator. However, this is all about measurements in a vacuum. Recall that light travels through a certain medium, such as water, more slowly than in a vacuum. So charged particles can move faster than light, but in some kind of medium. The proof of such FTL motion is Cherinkov's irradiation. When a particle moves faster than light in some medium, it polarizes other particles, or in other words, it repels or attracts. When the charged particle moves further, the electrons are returned, which causes the butte glow of the irradiation. One hypothetical subatomic particle could be another competitor to light in speed. In 1962, scientists considered the possibility of the existence of particles that would be faster than light with the inclusion of GR. But in their work, they noted that such particles could move faster than light from the moment of their appearance and not by increasing their speed, which is not contrary to GR. These theoretical particles were called tachyons. Unlike other particles, a tachyon has energy, but its mass at rest is imaginary, meaning it has a mass only when moving faster than light. It's also likely that an approaching tachyon will be invisible because light travels slower than it. In particular, it's also hypothesized to speed up when it loses energy. It's believed that a tachyon is formed when energetically strong cosmic rays hit the Earth's atmosphere. So far, the existence of tachyons has not been confirmed, and therefore light can be considered the speed limit at the moment. In addition, tachyons can lead to logical temporal paradoxes. For multiple observers, a tachyon can travel to the future and the past. So, if a tachyon can travel back in time, this leads to the classic causal paradox, for example, in which a traveler can affect his own existence and prevent his own birth or send a message to himself in the past. However, does superfast motion really lead to traveling back in time? In fact, faster-than-light travel is not necessarily the cause of paradoxes. For one observer, a spacecraft whose speed exceeds the light constant will travel back in time, so it will also land in the past before it took off. However, according to the physicist Sabine Hossenfelder, such paradoxes are possible from the standpoint of special relativity, not GR. Thus, another observer, for example, can move along with matter in the same direction, forward in time, which means that the ship for him moves only forward, and therefore cannot break the causal relationship and first land and then only take off. In fact, the second observer follows the entire process, and therefore does not see any logical violations that arrive from the perspective of the first observer, who believes that the ship is moving backward. So we can't simply accelerate to the speed of light. However, we know that light travels in space-time. What if we could bend space so that light travels a longer way than the object around which space is deformed? It sounds fantastic, but scientists are considering this space travel option. This concept is called the Alcubierre drive or warp drive. The idea of a warp drive is to stretch the canvas of space into a wave which should hypothetically compress the space in front of an object, such as a ship, and expand the space behind it. Thus, the ship will essentially move on this wave in a so-called warp bubble faster than light. Alcubierre's drive consists of three parts: the inner bubble or passenger space, where time passes more slowly than in the general space, and two outer parts, a shell of negative and positive energy and normal space without changes. However, warp drive requires a conceptual negative energy, which is impossible according to GR, but can exist in quantum theory in small quantities. This is one of the main problems of this theory. So to be able to implement it, it is desirable to find a method using positive energy. In 2021, astrophysicist Eric Lentz was able to develop such a concept. According to his model, such a bubble should contain a liquid plasma with a huge mass, about 10% of solar energy, and electromagnetic fields that would be located around the ship in the shape of diamonds. Such a bubble would be able to transport the ship, but only at a speed close to the constant of light, meaning that such a drive would not be able to accelerate to FTL. So far, it's impossible to confirm whether warp drive can exist without negative energy, as well as to start experimental work on it in general. However, if warp drive can work without the use of negative energy, then in the future, we'll be able to travel to distant planets much faster than with current technology. Another way that negative energy could hypothetically allow us to travel in time actually faster than light is through Einstein-Rosen bridges or wormholes. Einstein first came up with the idea of the existence of such tunnels from one place in space to another. It's believed that wormholes can be connected at gigantic distances of several million light years. However, although they have not yet been found, wormholes are very unstable, so they can quickly disappear due to negative energy. In addition, they're probably not as wide as we imagine. Also, because of this energy, wormholes must be small for a person to pass through. Therefore, until scientists find a way to keep both wormholes stable and large enough to confirm their existence, we cannot use this method for travel. Finally, quantum physics offers an interesting hypothetical way to transmit information at speeds greater than the light constant. This method of FTL communication is called quantum entanglement. In fact, quantum entanglement is an inseparable combination of two quanta that can exchange information with each other faster than light, despite the distance. Particles communicate by changing their state, for example, by changing their spin or energy. So during a long-distance travel in space, hypothetically, an astronaut could send a signal about possible life on the exoplanet under study, and this signal would reach the controller almost instantly. However, in reality, it is their variability and randomness that's the main problem that makes this concept of FTL information exchange unlikely. Quanta cannot be brought into a certain state to transmit any data because then the particles will break the connection with each other, and the particle whose state has not changed would show random results. So communication in this way would be impossible and probably not even reach the speed of light, because information cannot be transmitted at a speed greater than the light constant according to quantum mechanics. Moving at the speed of light or even faster gives us a serious advantage in space exploration. At the moment, we're not able to achieve this speed, but the hypothetical ideas of warp drive and tachyons, as well as the use of knowledge about FTL in different environments, can be an important step towards further research into ways to achieve the light constant. However, this is still in the distant future, so our priority now is to develop the technical knowledge we have so that our main goal in the study of space-time will be speed. There is a phenomenon in the field of astronomy that has intrigued and puzzled scientists for years. Hidden behind the glittering veil of the Milky Way, in the region of space we call the avoidance zone, there exists a gravitational anomaly so vast, so powerful, that it tugs at the very fabric of our universe. This is the Great Attractor. Although invisible to our telescopes, its gravitational influence is so great that it affects the motion of galaxies hundreds of millions of light years away, including our own Milky Way. But what is the Great Attractor? Is it a supermassive black hole? A colossally dense cluster of galaxies? Or something else entirely? And more importantly, what does its existence mean for us, for our galaxy, and for the future of the universe? In this video, we'll explore these questions, delving into the impact of the Great Attractor on our galaxy and the challenges scientists face in observing this elusive region of the cosmos. We'll also travel to the recently discovered South Pole Wall, a vast cluster of galaxies stretching at least 700 million light years into space, and its intriguing connection to the Great Attractor. So, will we eventually be consumed by this anomaly, or does it still serve another purpose in the grand scheme of the universe? Let's find out. About 4 decades ago, astronomers used the Parkes telescope to peer through the dust of the Milky Way. They discovered that our galaxy is traveling through space much faster than expected. Imagine, our Milky Way is traveling through space at 2,500 times the cruising speed of an airliner, 55 times the escape velocity of the Earth, and even twice the escape velocity of the galaxy itself. But where does such movement come from? Here's the mystery. The theory of our origin based on the Big Bang tells us that every point in the universe should fly apart from every other point. However, the galaxies on either side of us should be moving at the same recessional velocity, which should not result in net motion in the Milky Way reference frame. Net motion can arise from nearby clusters in the distribution of matter, such as a massive cluster of galaxies. The additional gravitational attraction of such a cluster of galaxies can slow down and even reverse the expansion of the universe in its immediate vicinity. But in the direction of motion of the Milky Way, such a cluster is not obvious. There is an excess of galaxies in the general vicinity and an excess of radiation visible in X-ray telescopes, but nothing that somehow seems large enough to explain the results. So what are we observing? A superdensity of pure dark matter? Or is the current theory of the origin of mass and motion wrong? Astronomer Alan Dressler of the Carnegie Institution used the first explanation, dashingly calling the missing concentration of matter the Great Attractor. But the mystery of the Great Attractor continues to baffle us. Despite our best efforts and the discovery of new galaxies, galaxy clusters, and new threads in the cosmic web, we still haven't found enough to explain our motion. The Great Attractor remains a mystery, pulling in our Milky Way and leaving us with more questions than answers. So over a vast expanse of space, some 220 million light-years away, there is a gravitational anomaly known as the Great Attractor. This region of space, located within the Laniakea supergroup, has such an enormous gravitational pull that it affects the motion of galaxies for hundreds of millions of light years, including our own Milky Way. But what is a great attractor? The term great attractor was coined to describe its gravitational influence, but it is not actually a single entity, but rather a region of space with a higher concentration of mass. This mass consists not only of visible matter like stars and galaxies, but also dark matter, an invisible and mysterious form of matter that by some estimates makes up about 85% of the mass of the universe. Understanding the Great Attractor is like putting together a cosmic puzzle. We know it's there because we can observe its gravitational effects, but we cannot see it directly because it's located in the avoidance zone, a region of space hidden by the dust and stars of the Milky Way. Despite these challenges, scientists have made significant progress in studying the Great Attractor. They have used various techniques, such as X-ray, infrared, and radio observations to peer through the dust and gas of the Milky Way and gain insight into this mysterious region of space. According to information to date, the Great Attractor is part of a larger structure called the Norma Cluster, which is one of the most saturated known galaxy clusters. It is in this cluster that the center of the Great Attractor is located. The Norma Cluster is moving toward the Great Attractor at an astounding speed of about 1,340 miles per second. So as we've said, the gravitational influence of the Great Attractor extends over a region of space spanning hundreds of millions of light years. This region, known to us as the gravity well of the Great Attractor, includes our own local group of galaxies, which is attracted to the Great Attractor at a rate of about 370 miles per second. Observing the Great Attractor is not easy. You can't just point a telescope at it and look. The main problem is its location. The Great Attractor is located behind the Milky Way, in a region astronomers call the avoidance zone. The zone is filled with dust and stars, making it difficult to observe the great attractor directly. However, it hasn't stopped astronomers from trying to unlock its secrets. They have to be creative in their methods, using different types of observations to peer through the dust and gas of our own galaxy. One of the main methods used is the observation of the 21-centimeter-long neutral hydrogen line. This faint line can be detected by sensitive radio receivers, allowing astronomers to see thousands of galaxies in blind surveys. The advantage of using radio waves is that they can pass right through the dust layer in the Milky Way, making our galaxy invisible. In the late 1990s, a group of astronomers began using the Parkes multi-beam receiver, an innovative instrument located in New South Wales. This receiver's unique sensitivity and field of view allowed increasingly sensitive radio surveys of the sky. These surveys, combined with data from new infrared surveys by the Hubble Space Telescope, have allowed astronomers to confirm the presence of nearly 80% of the galaxies found in the avoidance zone. The remaining 20% are too deep in the Milky Way to be confirmed with any existing optical or infrared telescopes. The zone of avoidance is a fascinating region of space. It's like a curtain that hides part of the universe from our view. But with the help of advanced technology and innovative techniques, we've been able to peek behind this veil and see hidden galaxies. The use of infrared surveys has been crucial. These surveys have allowed us to confirm the presence of galaxies that were previously hidden. It's like having a torch that can illuminate the dark corners of the universe. As we continue to explore and map the universe, a colossal structure known as the South Pole Wall has been discovered in the vast expanse of space. This wall, a veil of galaxies, dust, and gas, extends for at least 700 million light-years. It is so massive that it disrupts the local expansion of the universe. However, this huge structure, like the Great Attractor, remains hidden behind our galaxy, the Milky Way. It stretches from the constellation Perseus to the northern hemisphere to the constellation Apus in the far south. But despite its proximity and size, it's long gone unnoticed, hidden in a darkened sector of the southern sky. The South Pole Wall is a recent discovery announced by an international team of astronomers led by Daniel Pomeroy of the University of Paris-Saclay and R. Brent Tully of the University of Hawaii. The discovery was made possible by measuring the distances to 18,000 galaxies 600 million light-years away. Although the South Pole Wall is not visible to us, we can observe its gravitational effects. In an expanding universe, distant galaxies fly away from us. However, galaxies between Earth and the South Pole Wall are moving away from us a little faster than they should be, drawn outward by the huge clump of matter in the wall. Conversely, galaxies beyond the wall move outward more slowly, held back by the gravitational resistance of the wall. The South Pole Wall is an important part of our local universe. It's as large as the Great Wall of Sloan, but is twice as close to us. However, it still goes unnoticed because of its hidden location in the southern part of the sky. It is connected to the larger structure of the Laniakea supergroup, which includes the Great Attractor. All these structures are interconnected, affecting the local expansion of the universe and the motion of the galaxies. The Great Attractor, the South Pole Wall, and other such structures shed light on another enduring cosmic mystery: where we are going. Imagine you're floating down a river in a small boat without oars. The current of the river, like the gravitational pull of these cosmic structures, guides the motion of your boat. No matter how hard you try to control your boat, the current pull is too great, ultimately determining your path and speed. Similarly, our galaxy is like a small boat in a cosmic river, guided by the gravitational pull of massive structures such as the South Pole Wall and the Great Attractor. The future of our understanding of the universe and the Great Attractor lies in further research. Astronomers from Australia are leading several pioneering projects. The 2MTF survey, initiated by Castro, has already made a significant progress. Using the Parkes telescope, this survey calculates distances to galaxies, shedding light on the structure and motions in our neighboring universe. But the research doesn't end there. The upcoming Wallaby study, due to begin later this year, promises to push the boundaries of our understanding even further. Using Australia's advanced CSIRO SKA Pathfinder, or ASCAP telescope, this survey will allow us to probe deeper into the radio universe. In tandem with these radio surveys, the Australian Astronomical Observatory and ANU are embarking on a new optical survey called TAIPAN. This project will focus on elliptical galaxies, allowing us to travel to more distant regions of the universe. As research continues, our understanding of the universe is being challenged. Theorists are beginning to question the validity of the space-time metric we currently use to describe the universe. There's even talk of changing the general theory of relativity on large scales. As we look out into the cosmic expanse, we can't help but ponder the future of our universe. What does the accelerated expansion of the universe due to dark energy mean for us, for the Milky Way, for our great attractor, for the countless galaxies dotting the cosmic landscape? The universe is not static. It is expanding, and this expansion is accelerated by a mysterious force called dark energy. This force is so powerful it stretches the very fabric of space-time, causing galaxies to diverge from each other. But what does this mean for the future of galaxies and superscales? And what role does the great attractor play in this cosmic drama? Despite the expansion of the universe, the great attractor continues to exert gravitational influence on the galaxies surrounding it, including our Milky Way. So back to the burning question: will the great attractor swallow us up? The answer is no. Despite its enormous gravitational pull, the great attractor is not a cosmic monster ready to swallow us whole. As the universe expands, its gravitational influence will weaken. In the distant future, as the expansion of the universe continues to accelerate, galaxies that are currently attracted to the great attractor may begin to move away. The gravitational bonds holding the superclusters together will weaken, and these massive structures may begin to disintegrate. The future of the universe is a vast, ever-expanding cosmic sea with galaxies like islands drifting in the cosmic ocean, slowly moving away from each other. The great attractor, once a formidable gravitational anchor, will eventually lose its power over the galaxies around it.